started to recording. I just might want to make sure it's recording. This is recording. This is recording. Yeah, now it's recording. Yeah, we are recording. Anything else? Okay, no problem. So if you have any question, obviously again you have to stop me as you've been in the class. So I think we have had only 10 students at the beginning, so I asked once what would be the plan. So there are two ways we can do. We can just try either way whenever we are ready. So Michael, I make sure I send, if I have had time to write this before the class time, I make sure always post it to you or just link it to the same place that we have had on titanium. It's kind of hard for me because I can't guarantee how much I will teach. And it's just really not teaching one section, but I can say this is, for example, 5.2, and I'm just sending the 5.2 lectures, but later we can add it. So you have to really adjust your lecture note later. But that's a good idea to have it before the class time. And then the other way, if we just sometimes we haven't had the lecture note, I'll do exactly the same thing that I did in the class, right? So what does it mean? I just start to write on these whiteboard things, and then you can take a note, okay? But still, because we have the my handwriting things, I think you don't have to worry about if you didn't catch up. You don't have to worry about, because I'll share anyway the video with you, okay? Yes, this is yeah, this is 5.2. Yeah, 5.2. Yes, Rana, this is a 5.2. 5.2 is a long one. Yeah, is it just a long one? I think we need to do it today and the Wednesday class, then we can finish it. And then I believe by the end of 5.2, it's just in your test. I mean, in your take-home test. But because of this technology changing, I'm completely behind. So then I need to really find out what's just really your due dates, and then what do you have in next week. What I wish, if any of you can be responsible about those kind of email, the reminder thing, the checklist that I always send to you. If anyone can just be responsible or representative for your class and provide that list. So this is just really what we did cover and is the due date, and then what we couldn't cover and is you have to postpone. If someone can just really send an email to me and make sure we are all knowing what should be due this week, and then what should be just postponed for somewhere else because we were behind for some reason. Anyone can just volunteer to be the representative of the class for due dates. Only write down the same thing that I've done for every single week, and tell me what is due dates and what is just postponed, or something is wrong, or something like that. Because I know you have some group chat in your what is it, your club, or however you call it. If you can just really let me know any of the voices from your classmates. I need one volunteer.
Yeah, I mean, I can do it.
Brian, you are? Okay, thank you. So what we need is just really to know which due dates we need to list out for each week. And then if there is any question, like last time, if you have had any hard time to do any of the problems, for this week, for this week, for the practice quiz, and next week, the practice quiz, because it's in terms of the invertible or chapter 2, you should be fine. I mean, it's just invertible matrices or invertible transformation should be okay. But again, if you have any question about the assignment, especially if you have a really nice challenging problems in your assignments, I need to know which one is it. And then I like to make this discussion thing that we have had for voice thread just through the this Zoom, because this is a live discussion. Voice thread is just not live. So you just need to reply someone. So make sure you, Brian, let me know if you have any challenging problem, if someone can do any problem. The other thing is about the office hours. If the office hours is just 8:30 and then again noon, so for some reason you need individual office hours, you have to uh, yes, thank you, Brian. So if you need to make any office hours, please email me, and then the same way that we are making the class time, we can make individual office hours anytime through the day, not weekend, obviously. So if you want to make the office hours, if you have any problem that you need to discuss, it doesn't have to be really math problems. If you have any personal problem that you need to discuss, so request through the email. We'll make a meeting, just individual meeting through the Zoom. And I think I'm available all days except that just the weekends, but just let's see, right? So as I said, for making any office hours, you can always email me. It doesn't have to be right at 8. It doesn't have to be the class time, okay? So I'm available to make the Zoom for answering the questions too. Any comments? Any comment for me? Ready? Yes. Okay. This is going to be, thank you. So this is, I like to hear your voices. Okay, I feel just you don't listen to me or somehow you're doing something. So if you have had any question, please stop me. Thank you for answering through the message. That's great. So as I said last night, I just wrote this thing. I don't have really ready typed lecture notes for this course. So this is just ready for explaining through the lecture notes, but we can do either one. We can just write down at the same time too. So for this one, because I will post it online, so then you don't have to take a note. So this is a recap from last time, okay? So the transformation that we were looking to make it diagonalizable, if you have any transformation, what do you call diagonalizable? If you have just a basis that you can make that transformation to be diagonal matrix, okay? So diagonalizable transformation is the transformation that there exists a ordered basis that you can make that a corresponding matrix transformation to be diagonal matrix, okay? And then we have had one theorem that says, basically means something is diagonalizable if that basis is just having the property of transformation of the vectors is stretching the vectors, huh? So transformation of the vectors is stretching the vectors. So that means if you have a transformation of, how do I point to the things without writing? Brian, can you help me? I don't want to write it. I just want to point something. I just use highlighted. That's fine. Okay. So if
I'm actually not sure with OneNote. I just started using OneNote. That I probably think the highlighter is what I would do.
Okay, so this is what we call the eigenvalue of the transformation. So transformation of any vector is going to be stretching that vector. So it's just really scalar multiplication of that vector. So t is diagonalizable. T is diagonalizable if the transformation of that vector is lambda times of the same the vector. So this means you have had the set of your eigenvectors. You have the set of eigenvectors for the basis that you want to make the corresponding matrix to be diagonal matrix, okay? So the corresponding basis that I'm looking to make the matrix transformation to be diagonal has to be this way, This way means just to be diagram, to be eigenvectors, okay? And so the good things is whatever we have learned means if you have learned something about the matrix diagonalizable is going to be the same or similar for what we have linear transformation diagonalizable, right? So that's the next theorem. Next theorem says if you have this is diagonalizable, so means just your transformation is diagonalizable, basically means the matrix has to be diagonalizable. Just to remind you one more time, matrix is diagonalizable if there exists a Q. Matrix is diagonalizable if there exists a Q such that you can write that matrix in terms of Q inverse, invertible Q, BQ. So then later we just said this is just going to be that identity matrix for different bases, okay? So then that's just coming from our, what is it? This is coming from our previous course. Lambda is eigenvalues if determinant of matrix minus lambda I is 0. So that's called characteristic polynomial for transformation if you replace this one by transformation. So if you replace A by transformation matrix, so this is going to be characteristic polynomial for the transformation. And since the characteristic polynomial for transformation is really the main thing that we need to know, what is the solutions or just the roots for that characteristic polynomial, there are some things that we can just really point as a remark here about the characteristic polynomial. So the first part that I just wrote is everything about the review or what we have done before this class. So is there any question for this part? Is there any question for the review or something that we have learned last time? Okay, fine. So the one of the fact that I need to know, and it's just really nice to know because it says if you have n by n matrix, first of all, characteristic polynomial must have degree of n. This is fine, right? Because we just multiply something n times, so we just have the polynomial of degree n. So this is perfect. The other thing it says the leading coefficient is always 1 or -1. So the leading coefficient is always going to be -1 or 1, depends on whether n is even or odd. So that has really easy proof, but that's interesting to know that leading coefficient never have any number. And then the degree n, I think somehow is clear because your matrix is n by n. So as you see, the proof of this one is very short and nice because it's just really proved by induction. So if I want to say the matrix is, if I want to say the matrix is just by induction is 1 by 1. So if your matrix is just really 1 by 1, so then that works, right? So determinant of A minus lambda I is just really what you call characteristic polynomial, right? So characteristic polynomial is determinant of any matrix minus lambda I. And since it's just really a constant, so that's just really 1 by 1 matrix. So when you replace by that 1 by 1, so that gives you really a polynomial of degree 1, and it's just the leading coefficient is 1, right? So that's just works for n equals 1. And then if you just say this works for any n minus 1, the matrix of n minus 1 times n minus 1. So based on the induction, I want to expand this one to the n times n. So then if you just really use the first row to get that polynomial, so if you want to get the first row, so that should be the first element of your matrix minus lambda, and then you have the cofactor of that. So when you have the cofactor of that, so whatever left is, it has to be n minus 1 degree polynomial. So this by induction is true because we just said anything with the n minus 1 times n minus 1 is true. And then when you multiply it by 1 degree more, so that should be a polynomial of degree 1. And as you see, the coefficients for the original one which means n minus 1 times n minus 1 was 1. So when you multiply it by one more, still stay negative 1 to the power of n. Okay, does it make sense? Do you think we need to stop somewhere? This is just a 15 minutes thing. Do you need that kind of break again?
It's whatever's like comfortable for people.
What Rana said. Okay. So Solomon asked me to explain one more time what's just the induction steps. Induction steps, if we remember from the previous, 2AD courses, so it says if you have something which is true for n equals 1, and then you can just show the statement is true for k equals n minus 1, just implies your statement is true for k equals n, so then it's true for any n in the natural numbers. Okay, so that's a proof by induction, which says if you you have the size of your matrix equals I think so, 1. Okay.
Okay, thank you.
The only problem about the lecture, so somebody asked me whether I can send it before the class time. I hope I can. Okay, so I will try my best to have this thing before, but I'm thinking which way is working better, right? So that's what I'm not sure. So if I write down the lecture note entire and explain through this lecture note, or just write down as I'm explaining as it was just really in class time. So this is what I need for your feedback. To make sure at least some sort of statistics to make sure which way is working better. So the way that the lecture note is written by my hand and then explaining through that, or I just write down during the lecture. So I know that that's really take time to write down as I'm just teaching, but we have done the same thing for 9 weeks, so we should be okay. So anyway, we'll find out which one is working better. But anyway, because this is right here, I try to provide the lecture note and the videos at the same time for you. And that's just really advantage of having this type of class, because if for some reason you have to leave for any emergency case, and for some reason you don't have any question or concern about the lecture note, so then you can just watch it later and you can just, but I think that's just really not a good idea. I don't like that idea. If you just sleep right now or do your something else, and then you have to spend extra time to come back to listen to the lecture and check everything. So it's better to be live as we've been for entire 8 weeks. Okay, so just about the induction, because Solomon asked me to explain one more time. So this is the statement, the basic step, which says if the some statement is true for n equals 1, and then excuse me, so if this statement is true for n equals 1, that means your matrix has to have a size of 1 times 1. So determinants, the question asked me to show characteristic polynomial. So okay, so characteristic polynomial has degree of n and leading coefficient of -1 to the power of n. Okay, so that characteristic polynomial means determinant of a minus lambda I. So that's what we call characteristic polynomial. But as long as the a is just really 1 by 1, I did not do anything. It's just really determinant of a constant, which is exactly itself. So that's fine for the basic step. For the induction steps, if the statement is true for n minus 1, so let's see your polynomial has the degree, so you have the matrix of n minus 1 times n minus 1. So we know already the statement is true means the degree of the polynomial is n minus 1, and then we know the leading coefficient has negative 1 to the power of n, or is plus minus 1. Okay, so then this is my whatever is the goal to show. So if I have 1 degree more, so which means your statement is for the matrix of n times n. So that means you need to expand your determinant of a minus lambda I. So that a minus lambda I, because it's expanding for the first row, so your matrix looks like this. So this is a11 minus lambda, and then it's just really the rest of elements that you have had, but that's just because the entire is n minus 1. The leftover is going to be n minus 1 times n minus 1. So the main thing was n minus 1, but since you just cut off the first row and first column, so this means the entire thing has to be n minus 1, which by the assumption is n minus 1 degree, and it has leading coefficient of negative 1 to the power of n. So when you multiply it by 1 more, it's going to be degree of n, and it's going to keep the leading coefficient still plus minus 1. Was it fine? Solomon? Okay. Any other question? Any other question? Okay, go ahead. Did you ask the question, or you're trying to write down? Not yet.
Sorry, I'm still typing. Sorry.
Why you don't just say? That's better.
Oh, okay. Yeah, that's so much.
Yeah, you know, because I thought you don't have something available to talk. So if you just say it, because this is recorded, and then I don't read the problem. I don't read the problem at the same time when you ask the questions. So then people, when listening later to the recorded one, they don't know what's the question that I'm asking. So if you have a question, don't type it. It's better for your recorded video to be really live as I'm explaining.
All right. So the part below saying the polynomial of degree n minus 1, shouldn't the leading coefficient be
negative 1 to the power of n minus 1? Okay, so this is right.
Yeah.
This is negative 1 to the power of. Yeah.
For technical. Yeah. Thank you.
Thank you. Thank you. Okay. Yeah, that's perfect. Okay. So the other thing that we need about this characteristic polynomial is when we have a polynomial of degree n, that's just in algebra, right? So this is fundamental theorem in algebra, which says we must get at most n eigenvalues, right? So at most n roots for polynomial of degree n, it makes sense, right? So this is just really something that we know, because the characteristic polynomial is degree n by part A. So it has to be at least n roots, which is eigenvalues for us. Make sense? So something we are really interested to know is about similar matrices. Why? Because we know when we have a matrix transformation with different bases, they are similar matrices. One more time. If I have a matrix transformation, let's say for beta, and matrix transformation, let's say for beta prime, right? So if you have two different matrix transformation, one of them is for basis beta and the other one is for basis beta prime. So these two are similar based on one of the theorem in, I think it's 2.14. So these two are similar matrices for different bases, okay? So that's interesting to know. If they are similar matrices, they have the same characteristic polynomial. So then they have the same roots. So then they have the same eigenvalues. So then I don't have to worry about. So if the matrices are different, which means they are similar matrices for different bases, I know whatever I get from determinant of A minus lambda I is going to be the same thing. Make sense? So no matter what is your basis and then what is your characteristic polynomial for that determinant of A minus lambda I, still your polynomials is going to be the same, the roots is going to be the same, so you get the same eigenvalues, okay? So it's just regardless of your basis, okay? So that's just proving simply when we have two similar matrices. Should I remind you what is similar matrix? I said at the beginning, right? And that's just really what one more time over here. So one more time over here, it says if you have A and B are similar means this. There exists a Q. So this means there exists a Q invertible such that you can write B as just Q inverse A Q. So this means they are similar, okay? So what's the goal? The goal is to say the characteristic polynomial of A and B are the same. So means you just say if you have characteristic polynomial of the B, so means determinant of B minus lambda I or Ti, you're supposed to show is the same for determinant of A minus Ti if the A and B is connected by this way, right? So if A and B are similar in this way, determinant of B lambda I, which is characteristic polynomial for B, is the same as determinant of A minus lambda I, which is the characteristic polynomial for matrix A. So that's just really just between these two to show, yes, that's just really simply coming from the way that is defined. So because the B is just really the Q inverse AQ, and then you have to subtract from the lambda I. So that's just really what we call characteristic polynomial. So this is just really one techniques to factor out Q inverse from both sides, and which says if you have a Ti and then you multiply by right side by a Q and Q inverse, so these two are equal because it seems is just really multiplying by I. So this seems is just really multiplying by I. Do you agree with this one? From here to here. So let's say if you have a Ti and you like to multiply by a Q from the right side and then by Q inverse from the left side. So this is going to be a Q, okay? So I times anything is going to be itself, and then if you just factor the constant, this is Q inverse times Q, which is just really T. So this is T times I is really the same as writing this Q inverse TIQ. So that tells you why from here to here is true. And then the rest is just really factoring out. I'm factoring a Q, I'm factoring the Q inverse from the left side, and then I'm factoring the Q from the right side, and then it's just really determinant of product is product of the determinants in next row, and that's just this one left. Is that okay? Why the middle one left? Is that okay? Why the middle one left? Why this middle one left? Huh? Let me change my pen. Why it doesn't work? This is still on highlight. For some reason it doesn't work. Anyway, okay. So because of determinant of Q and determinant of Q inverse are reciprocal, they cancel out. So then you have only determinant of A minus T left. So this means what I wish, right? So determinant of B minus Ti equals determinant of A minus Ti, okay? Any question? So one more time, which I wrote the variness over here, it says if you have two different bases, you might have two different matrices, but you don't have different eigenvalues or different characteristic polynomial. Why? Because these two matrices are similar, and we just now proved it. They have the same characteristic polynomial, so they have the same roots, so they have the same eigenvalues. Make sense? Does it make sense? Mm-hmm. Thank you. Thank you. Okay, so that's just really to say, okay, so if right now we have, hey, Amber, I have you. How are you? So if I have what we call determinant of the a minus lambda as characteristic polynomial, so then I can just really define this is determinant of that transformation. It's just really the terminology. We transfer the determinant from the matrix to call it determinant of the transformation. So if you have a transformation, what does it mean when we say determinant of that transformation? Means the determinant of corresponding matrix in any beta. Okay, so that's just definition of what is determinant of a linear transformation. Determinant of corresponding matrix, and that's it. And I have no idea, it seems something is wrong. Do you see? So let's just pause for 1 minute. Let's just pause for 1 minute to see why it's the whole thing black. Sorry, white. So I don't see it. This is looking one more time to the shade to the screen. I will close my lecture note and see why everything glitch. Okay, so now this is fine. Yep, this is fine. Now I have to go back to your Zoom and then start to share one more time the screen. And then now go back to the lecture note. Okay, now I'm fine. Okay.
Can you go back just a little bit, like a little bit further up? To the, it was the, okay. Yeah, that's fine. It was the number 4. Enables us to determine the characteristic and polynomial for linear t.
Yeah, since this is unique, if it was different for different bases, we couldn't really see what is the determinant. I mean, it doesn't make sense to define what is the determinant of the transformation if it's different from different bases. Since we now find out, okay, no, it's not different. So as long as they are symmetric matrices, they have the same polynomial and they do have the same determinant. So then we define this is going to be determinant of the transformation. Move on? Should I move on?
Yes.
Yeah, I think you're good.
Okay. So this is just an example. This is just an example. It says the transformation is defined and the matrix corresponding that for a standard basis is going to be right there. And which is just really writing the A's all the way here, writing the B's here, and then C's here, and then this is your matrix in the standard basis. And this is the determinant of the corresponding matrix transformation. So if this is the determinant, that is going to be the determinant for the transformation itself. So determinant of matrix transformation is called determinant of the transformation, and that's it, okay? Some nice results. We don't prove it because it's just really applicable, I will say, points that we have it over here is simple. What it says, for two different matrices, for two different linear transformation, If you have t is invertible, I don't have any problem to say determinant of that t must be just non-zero. That's exactly what we actually, who was it? Madeline asked me at the beginning, and Rano says I've done the same thing, and everyone says I've done the same thing, because that's just really true, right? So if the t is invertible, determinant of corresponding matrix is going to be determinant of your transformation. So that is non-zero, means your t is invertible. So it's a lot easier than checking onto and one-to-one. As long as determinant of corresponding matrix is non-zero, so that is invertible transformation. And this is nice to know. So that's exactly like the matrices, right? So if you have determinant of t inverse, is just really reverse or reciprocal of determinant of the t. So determinant of inverse function is reciprocal of your original transformation, like exactly what we've seen in your matrices, okay? And this product here, number C, it means composition for us. But as far as when you plug in the corresponding matrix, so that's just really product of the corresponding matrices. But that's interesting to know that goes exactly same property that we've seen in determinant property of matrices. So determinant of composition of TU or T times U is determinant of T dot or multiplied by determinant of the U. So that's interesting. And the last one, that's exactly what we just expect to be. If you have the transformation right over here, so characteristic polynomial is determinant of t minus lambda I, but that means really basically plugging that t to be your corresponding matrix transformation. And that's it, okay? So here both of them are functions or linear transformation. Here both of them are matrices. So these two are matrices, but these are really the same thing for any basis, because that's similar matrices, okay? Any question here?
Yes, Professor.
Mm-hmm.
If we're trying to show that a transformation is invertible, would it be sufficient to say that since the dimensions are equal to each other, then it's invertible?
No.
Okay.
That's just really good. So I was planning to make this one as a extra credit or challenging or some discussion. I love to put this question because that's just I think this is 4th or 5th times I'm hearing this one, and because of that theorem, right? So I know where the question is coming from. Because of that theorem, it says dimension of the V equals dimension of the W if and only if, right? What was it? Can you remember what was the theorem?
Was it isomorphism or?
Yeah. So the T is isomorphism, right? So then this says, okay, so as long as I know that they are the same dimension, so this is going to be isomorphism, means is 1-to-1 is on 2, so it's invertible, right? So that's just what the theorem says. But and then for the exam that for the quiz that we have had on Wednesday, there were just really something that is just from polynomial of degree 2 to the polynomial of degree 2, but that was just the dimension of both sides was the same, but that's just not isomorphism. It was just one example. I think was the C part. I didn't post the solution yet. And that can't be true. So look at your transformation to be transformation of 0, right? So if you have polynomial of here transform to the 0, this is not invertible. So if you have the transformation to be something like I don't know, just really something that is not invertible matrix corresponding by that, so I will say x times px. So if you don't have the matrix corresponding by that to be invertible, so it's not invertible. As just really 0 is really good example. Even though the dimension of both sides are the same, it doesn't mean is invertible. And I like to just bring this one in discussion to see why that even is it the theorem wrong, or we are thinking what is missing point here, that we have the dimension of these two sides the same, but that's not isomorphism, or is not invertible, or is not 1-to-1 and on 2. Okay, so that was thank you, Solomon. It remind me we have had these questions or confusion a few times. Anyone has any idea? Anyone has any idea?
Yeah, there's if you think of like the linear transformation like geometry, you can look at like, you know, something happening in the R2, right? That's pretty easy to visualize. If it goes to zero, if everything goes to zero, there's no eigenvalues in there, and there's no way to like reverse that. You like lose the information, right? You don't have any ratios that are preserved that you can just reverse those ratios and move them in a different way to make it all better. And that happens anytime, you know, and even if it didn't all go to zero, even if the whole space went to a line, well, that would end up being kind of the same thing of like, you can't turn a line into the whole, the same plane that you had, right? You can, that wouldn't be a linear transformation anymore, right?
Mm-hmm.
To go from like a plane, or from like a line to a plane, right? It takes a little more than that. So there's some good YouTube videos on it, but like anything with like animations can kind of help. Or like even if you just draw it out, you might be able to see it.
Yeah, that's true. Any other question? Any other question?
Just one question with the theorem saying the dimension v is equal to dimension w, because on my notes it says that v, the vector space v, is isomorphic to w if and only if the dimensions are the same.
Oh,
Is
okay.
that like is that the same thing as saying that T is an isomorphism?
Yes, it's the same.
Oh, okay. All right. Okay, just double checking. Thank you.
Thank you. That was a good point. So that's just really the same thing. Yeah. So if they are, if there exists any T from V to the W, and then dimension of V equals W, T's isomorphism is the same as to say V is isomorphism to W, or the T is isomorphism. So it's the same thing. Yeah. Any question? Move on. So this is, I don't know whether you are all okay. Do you see my, yeah, so you see my note, right? Okay, so for maybe I will say for just while we want to say, okay, whatever we have done for the transformation is going to be exactly one version in matrix. And then whatever you have done in matrix version is going to be in terms of the transformation. I mean, the terminologies, the eigenvalues, eigenvector definitions, diagonalizable. So all those information that you've received in your previous course is somehow replacing that matrix by transformation. So you're good to go. So this is what it is trying to say over here. So if you have your yes, Brian. Yeah. So if you have what is given basis and you try to make your transformation to be diagonal, so what would be the matrix version of this question? So that means is it possible for matrix of A to write or to find the Q such that the Q inverse A Q is diagonal matrix? Okay. So if in the transformation version, we are looking for a basis of the beta such that the transformation matrix is diagonal matrix, in the matrix version means we are looking for a Q such that Q inverse AQ is diagonal. So that's just really different the version of definition in diagonalizable that we've seen in previous course when we need it right over here. So if this thing is possible, that means A is diagonalizable, and then we just really need that left multiplication transformation to just always connect whatever concept that we have in this linear algebra and what we have had from the matrices in previous course. Okay, so then A is diagonalizable means corresponding left-hand multiplication is diagonalizable. So this means A has to have a basis which are your eigenvectors, the set of your eigenvectors, okay? And the claim is this Q exists or does not exist, then we can just build that diagonal matrix of the D that we are looking for. If you remember from the previous course, you know what it is. It's just to remind you what we have done in previous course to build that Q and then corresponding diagonal D matrix, okay? So this, if this Q exists, is just really make the eigenvectors to be columns of your Qs, if you remember in previous course. So you just get the determinant, step number 1, get the determinant of your determinant of A minus lambda I equals 0, and then you find your lambdas, and then you just get the corresponding vectors, and then if you set that vectors to be the columns of the matrix Q, then that's just really that invertible matrix that you were looking for. And what is the diagonal matrix that I'm looking for? Is just setting this, lambdas to be, setting these lambdas to be my, diagonal entries, okay? So that's just what we've seen in the previous course. And the notation wise, if you remember, Q inverse AQ equals by diagonal, and that's how you write it in the previous course, and that's fine. We can write it exactly the same way. So the process of finding the Q or building the Q was get the determinants that equals 0, find the lambdas, find the corresponding vectors, and set them in the columns of a matrix and call it Q. So this is just one example to remind you, you have done this process in previous course, because this is not about the transformation, it's about the matrix. I have a given matrix. So step number 1 to solve it is just get the eigenvalues. So then you have to make the determinant of this main diagonal minus lambda, which is A minus lambda I. And then you solve it for that. I actually expanded for the last row because it was easier. These two are zeros, so this is just easier for expanding to the last row. And then I've done this calculation, and then I got my lambdas. So then corresponding by each lambda, you get the eigenvectors, right? So corresponding by each lambdas, you get the eigenvectors, and these are my eigenvectors. So as I said, all I need to just do is put these vectors to be columns, and then that's just really corresponding to the 5. So I have to keep the order. The order really matter here. As we know, it's just really ordered basis, right? So if you switch these two is fine. If you switch these two is fine because they are both for 5, but you can't just do it with this one, okay? So this is corresponding to the lambda equals 1, so it has to be in last column. Or you can just put it first, you can put it in the middle, but you have to be careful. Corresponding entries of the whatever is in the D has to be vector in the Q, and the order really matter. Any question?
Yeah. So when you compose this is a change of basis matrix, right? And when you compose it, you have the corresponding eigenvalues. So like you have an eigenvalue of 3 in column 1, you have an eigenvalue of 3 in column 2, and 5 in column 3. And then you need to put the corresponding eigenvectors in their corresponding like columns.
Mm-hmm. So let's see, you have decided to make this one to be, these are all 5s, right? So this is 5, this is 5, this is 1.
Yeah.
Okay. So then for the 5, I have 1, negative 1, 0, and then I have 1, 1, 0, and then for the, 0, 0, 1, and then I have 0, 0, 1. Okay. So this is for the 1. I have to switch it exactly same way. Again,
Okay.
stuck. My pen, sorry, my pen is stuck. Okay.
That's interesting that you can, when you get the 2 eigenvectors for an eigenpair, for an eigenvalue, that you can switch the columns.
It gives you the different, yeah.
Yeah, it's interesting.
It's really interesting. It will be more interesting when we go to the next step of diagonalizable, which is when we don't have enough eigenvectors, and then we try to build a new one by the method that we have tried somehow in previous course. If you have had that last chapter, so it will be more interesting how this order changed the result. That is just Jordan canonical forms. This is really fun. Any other question, guys? Any other question?
Yes. So for the vectors, the eigenvectors that correspond to the eigenvalue, if we get two eigenvectors for the eigenvalue, do those order matter? I don't think so, right?
No, it doesn't matter.
Okay.
It doesn't matter. So for now it does not matter. But again, when I go to chapter 7, because right after this one I'll go to chapter 7.1 and 2, which is just next level of diagonalization, and we call it Jordan canonical form. And you will see, and I hope at that time most of you try to just do it with the calculator. So you will see even in that, no, it does matter. So even in that chapter of 7, that is Jordan canonical form, if you switch that to, you don't get what you wish to get. So then you have to test which way is working. Which way is working.
Okay, thank you.
For now, yes, it doesn't matter. Okay. Any other question? I don't know why you do you have my camera? Anyone has my camera? No, you don't have, right? Even it's on, you don't have the camera. Anyone has the camera?
Yeah, I have your camera on.
Oh, so means do you see me or you don't see me?
I do. I see you, right? You're like in a little box right on top of the
Okay, so that's
You-
great. Okay.
Yeah.
You have the option of seeing everybody in the class, and then since you're the host, you're the first one.
Okay, perfect. Oh, so that's why I don't see myself, because I closed that one. Okay. I thought my camera is on. Oh. Kimberly doesn't see me. I don't know why.
Oh no, I do. Did I type it wrong?
Yeah.
Yeah, sorry, you can see. Oh wait, sorry, wrong Kimberly.
Okay.
Yeah, I'm Kim.
Okay.
Sorry.
Okay. As we know, finding that cues, that was just really your questions, right? So how about if I switch it, huh? So that's just says right over here. So this is just not unique, right? So writing the Q and writing the D is not unique, because for several reasons that you said, we can switch the order of this D, and Q, and then, so that's just not the unique. But the lambdas are unique. Again, eigenvectors are not unique, right? So you can have any scalar multiplication of these vectors, right? So if I just write it to be what is 2 to 0, still is eigenvectors, right? So if I just write it 0, 0, maybe 10, that still is eigenvector, because any scalar multiplication of this is going to be eigenvector, okay? So that tells us Q is not unique, right? And the D depends on the order. It might be just different, right? But again, for now, for this section, as long as we just put the corresponding column of the eigenvalues to the eigenvectors, we should be fine. But for next step, which is the next level of the diagonalizable, we need to be careful about the order more, okay? Even though if they are the same eigenvalues. So one more time is reminding us, whatever is just related, whether something is diagonalizable or not, is nothing about the number of eigenvalues. So it's just really the number of eigenvectors, right? So number of eigenvalues for this problem was 2, but since number of eigenvectors was 3, we were fine, right? So we need to get enough eigenvectors, not eigenvalues, right? So you can have repeated one, it's fine, okay? So if you have a repeated eigenvalues is fine, as long as you get eigenvectors corresponding like that, okay? And that's just one theorem to say the main issue is, do we have enough eigenvectors? do we get enough linearly independent eigenvectors? So this is just telling about the result says, if you have exactly different eigenvalues, corresponding with those eigenvalues, you will get linearly independent eigenvectors. So if you have k many, where's my highlighter? If you have k many eigenvalues and corresponding by each eigenvalue, you can get one eigenvector. So those eigenvectors are going to be linearly independent. So there is no relation between, never ever there is any relation between vector that you get from this 5 and then 1. Okay, so the eigenvectors that I get from different eigenvalues are linearly independent. And that's just a really short, nice induction proof about why this is just true, why eigenvectors corresponding with different eigenvalues are linearly independent. So this is just a proof by induction. So if you have only one eigenvalue, it's going to be certainly linearly independent. And then if you consider you have k minus 1 eigen vector for k minus 1 eigenvalues, so that's just true by this definition, or the way that we define to be something eigen value. So then since we consider, actually what we are looking for is just to show the linear combination of k many vectors is 0. So then all of those variables or coefficients of a k must be 0, okay? So all I did is just really make this multiply by lambda k. So then it's just really same equation from here to here, and I just multiply every single one by lambda k. And then same thing over here. So what happened for here? So lambda 1 v1, lambda 2 v2, and lambda k vk equals 0. And then I just subtracted. Since the v1 to vk minus 1 is linearly independent by assumption of my induction, so then all of these numbers must be 0. All of these coefficients must be 0. So then I have to set AI is equal 0, okay? So AI is equal 0, all of them before the k minus 1, I just need to say the k1 is 0. So that's just telling this k is 0. Does it make sense? Any question about this induction proof? I give you a minute to just look at. Anyone? Solomon, Brian, Juan, Kimberly, any question, guys? Nico?
No, I'm good.
That makes sense? Okay. Thank you, Rana. Any other? Okay. So this is just really simple corollary from the top, which we just say if you have different eigenvalues, corresponding eigenvectors are going to be linearly independent. So that's just telling if your dimension of your vector space is n, and then you get exactly n many eigen, what is it? N many eigenvalues. So then that is going to be diagonalizable. It's just really like when you have a 2 by 2 matrices, right? So you get just 2 eigenvalues, that's just going to be diagonalizable. If you have 3 by 3 matrix, so then you need 3 eigenvalues, and then corresponding by each one you get 1 eigenvector, then you are good to go, right? So you have enough vectors because you have n many. So that's exactly same thing when we go to the transformation. The size of matrix is n by n is the same as to saying the dimension of your vector space is n. So then you get n different eigenvalues. So then it's going to be for sure diagonalizable, because for each one you will get 1 eigenvector. They are linearly independent. So then you are good to go for making Q. Okay. And we have had the same thing. I mean, the same statement for matrices in previous course. This is just really changing that statement to the transformation. Make sense? Do I have time? Yes. Any question? No? No question? So then we know from the previous course was true for the matrices, and now the question is for the transformation. Even if you have a dimension of n and you don't get exactly n eigenvalues, do you still have diagonalizable? Is it just really no forever? We said no. This number of eigenvalues has nothing to do with diagonalizable. Number of eigenvectors is what I need to check to be enough, right? So the answer is yes, we need to check one more time how many vectors we get corresponding by each eigenvalues, right? So this is the cases might happen. This is just how we can just get, actually these two examples I think is really clear. So you have had, for this one, you have repeated eigenvalues. So which lambda equals 1 is just, there's something wrong. Lambda equals 1 is just your repeated values. And for this one, lambda equals 1. And then is it diagonalizable? So is this one, I mean, identity matrix diagonalizable? Anyone knows? No.
No. I'm not sure.
Kimberly said yes. Why? Michael, no?
I said, yeah, I don't think it is.
Kimberly?
Because determine is different than zeros.
Okay, that's a very good point. Diagonalizable, is there any relation between being diagonalizable or being invertible? So then is there any relation between diagonalizable or determined to be non-zero? So
yeah, totally. I mean, when you go back to the systems of equations interpretation of like being invertible and doing the row reduction, right?
okay. So that's a very good question. Actually, you have it. I think it's just one of your homework or just practice quiz. So if T is invertible, and actually I think it's just one of your group work too, right? I think it's the next one. So if T is invertible, then T is diagonalizable. And then it was just one question, and then the other way. If T is diagonalizable, then T is invertible, okay? So for, these are true false problem. These are true false problem. And actually none of them are true. And none of them are true. You can just check the homework or group work. And then, so that's just one really nice condition that is getting the relation between diagonalizable and T being invertible, whether the lambda equals 0 is just your, what is it? Lambda equals 0 is your eigenvalue, okay? So I think it's problem number 8 of your assignment, if you check it. So you'll prove such a this thing, but no, there is no relation, okay? So then if, so for these two examples, if I just say lambda equals 1 is repeated, is it diagonalizable? So then the question is, can I get two vectors to fill out the columns of the queue? Or is it corresponding by lambda equals 1? Do I have enough eigenvectors? And same as over here. So always the question is not how many eigenvalues do I have. So do I have two eigenvectors to make that Q matrix, okay? So that's just the main concern, that how many eigenvectors do I have? So if we have enough means really n many. So if the size of matrix is n times n, so then we are having the diagonalization. If not, no, okay? Any question? Any question? No? This short thing is the last one that I'm going to add right now. So in which cases this diagonalizable fail? So which cases you might have that you say this is not diagonalizable anymore, okay? So that's just one example, which I have it on top. This is just same example over here. This is whenever your eigenvalues is repeated, okay? So if your eigenvalues is repeated, so for this one, remember, if you have lambda equals 1 equals your just eigenvalue, if lambda equals 1 is your eigenvalue and repeated 2 times, and your matrix has a size of 2 by 2, I can't get two free variables from one matrix. There's no way, am I right? So there's no way to get two free variables. If I plug in 1, so it's 1 minus 1 is 0, 1 minus 1 is 0, and then 0 and then 1, okay? So this is going to be free variable, and corresponding by 1 eigenvalue, I could just get one eigenvector because I have only one free variable. There is no way to get two free variables, two vectors. So then that's not possible to be diagonalizable. For what I'm trying to say is, for 2 by 2 is super easy. Why? Because if you get repeated 1, there is no way to get enough eigenvectors, because there is no way to get two free variables. If you have two free variables, you will get two eigenvectors, so then you can make that Q thing, so you are fine. But if it's just really 1, so there is no way to build 2 of them. So then that's not diagonalizable, okay? So for repeated lambda, that's one case that we need to be careful. But so as you remember, for this one, it was fine. I mean, even, do you know why it's getting why? Okay, so I'm too fast. So for this one, if you have repeated, if you have had repeated 5, and then you got corresponding by 5 two eigen vectors, so you were fine. You were just really totally fine, because you got two free variables, because you have had really 3 columns. So then you could just make 2 free variables. But when 2 by 2 you have only one eigenvalue, is just really at most one eigenvector, so there is no way to be diagonalizable, because you get only one free variable. And the other thing that you might have is, from the beginning you don't have enough eigenvalues. So that was just one example that we tried last time. This example was no eigenvalue, no real eigenvalues. So there was no real eigenvalues. So I don't have any eigenvalue to start with. So then I'm done. So that's not diagonalizable, okay? And then to get to the theorem, actually, I'm going to stop here, but to get to the main result. So if your determinant of t minus I, there is no way to factor it completely. So as long as you can split your, your polynomial, so then you can get the roots of your polynomial, so then you can have your eigenvalues, right? So as long as you can just completely factor this polynomial, so then you have your solutions. So this means this is just really means you have enough eigenvalues, and then corresponding by that you have enough eigenvectors. So as long as it's factorable, means diagonalizable. That's just the point I want to continue next time. But right now, as I said, I want to stop. Do you have any question or comment for me? As I said, since I have most of you right now, as I said, my plan is just come, to be online at 8 to answer the question as we have had in the class time, 8 to 8:30. And then I will continue this video about 15 minutes after the class, again, to answer your questions, okay? So still, it doesn't mean I don't have any other, office hours. I do have any time that you email me to say, I want to have some questions about the homework. I will be just available. I will make the, for some reason, I can't be. Brian, can you help me? Where is I minimize my comments. I don't know where they are now. And somebody is typing anything. I'm missing that one. So let me. Okay, so you're typing. Okay.
Are you trying to find the chat?
My comment, yeah, I found it.
So, okay, it's right at the bottom.
No, it wasn't. It was on top. Because just different format. Okay. Anyway, because I minimized it at the beginning, I couldn't see the entire page. So now I can just bring it over here. Okay. But it says, is it possible to get these notes posted on Zoom? Then why it goes down? I haven't, there are many questions asking at the same time. Can you please, if you can just answer your, ask your questions as you unmute your, your mic. I can just really hear. Okay, is it possible to get the notes? Yes. But not just really 1 week ahead, it's just really last night. There's a bit lag sometimes. Why? Oh, for writing the note? Okay, yeah, exactly. I agree with this. The other question was, I agree with everyone else. That was Stephanie. Where is the other? Okay. Nicholas for the exam.
Sorry, I think speaking for everyone, if we can have the notes before class, that way while you explain it, we're not trying to just copy the notes, we're trying to understand what you're trying to say with the note.
Yeah, this is just great. At the beginning of the class, I mentioned about this. There are 2 options, and still I'm just really getting feedback from you. I'm fine with either one. Write down the note the night before, because the problem is I didn't have any iPad or laptop. Now I have a Surface Pro, just brand new. I bought it in about less than 24 hours just to find out how I can explain something to you, because I didn't have any type of this thing I can write it. So that's why my lecture note is complete. It's just really 1 page ready for right now today, and that's it. Okay, so we need to plan ahead to just post this type of thing if the decision is just really have the note ready as I did today and explain through the note. Okay, but if you decided to just really know, I just want to write down as you are writing, and really same thing that we have done in the class. So then that's just a different base. Yes, that's just really, I will for sure provide for you. Okay, so if I find out how I can work with this new toy, then I will just provide the lecture notes before, and then the video is recorded. So that's just everything is ready, and I agree with you. That's easier. Fine. So you are fine with this way of writing?
I think this is the best way to do it, because otherwise you would still be writing and you would have to scroll up in order to continue to write, and it would still be too fast for us.
So then that was just really many advantage for the students. They don't have to go to school. They don't have to take dress. You can do your lecture in your bed, and then your lecture is ready, so you don't have to take the note. So it's just really great way. I'm hoping you just really use this, saving a lot of time to just watching the videos one more time and just figure out what it is, right? So is really saving for you, at least for this 3 units class, coming to the campus and just making the lecture note and just videos, everything is ready for you, is saving about 1 hour or half, just because we just made it in this way. Okay, I'm hoping you can use this saving time not to sleep more, just to do your homework, or to just practice more and watch the video one more time if you have had any question. And again, if you have any thing that you need to make it in person, individual Zoom meeting or office hours, or however you want to call it, email me. And then if you are happy, I can just really have any discussion, like any problem, challenging problem. That's Brian is responsible for this thing. So we can make a Zoom meeting for only one problem for any time that you all agree with that. Okay.
Okay, and when can we expect the recorded video and the notes to be posted on Titanium?
That's a good question. I think if it depends on how long is the video. If you need it like this, it seems the Titanium takes about last class, it was 2 hours class, and it was about maybe 4 hours that I could get it. It's not available right away. That's what I know. So it should be really same day, a few hours. It's not available right away on the cloud, sorry.
Okay, that's fine.
So it's same day. That's what I can promise. What's about the exam number 2? I mentioned in the email, exam number 2 on Monday is going to be just the take-home one, which is the 30%. And exam number 2 in the class, I don't think I can make it for several reasons. But my plan is to make just really one more exam, and that's exam number 3, and at the end of when we come back to the school. So the worst case scenario is just we don't come back to the school. Then we have to make it exam number 3 only on the online one. That's just the plan.
Professor? Since we won't be having the in-class midterm, or you won't be giving it to us online, and it'll just be the take-home part. Will the take-home part of the midterm will the take-home part be 100% of the midterm?
No. It's 30%. No, we can't. Sorry.
So are we going to be given a different option to make up those points that we would have got on the in-class midterm? Does that make sense what I'm asking?
Go ahead.
What I'm trying to ask is, since we won't be given the chance to get those points in the in-class midterm, will we be giving a different option to, to boost our grade?
You see, this is going to be just really one midterm that we have had 100%, and then another third midterm, which is just really exam number 3, which we hope to come back to the school. So that's just another 100%. And then this, what is it? The middle one is going to be 30%. So means the worth, so whatever is just the number on exam number 2 is about 1/3 of the other exams that we do in the class. Does it make sense? I don't think we have any other. I mean, what's the reason I can't just give you any other option? Because you're doing really great, and then that's just a lot of work for you. If I'm adding anything, any extra assignment for you, that was just really 70%, that's just going to be really a huge amount of work to do. Okay. So, but still, I that's for now, that's my decision. We can just really, the worst scenario is we don't come back to the school. That's just really the worst one. But that's just really making 2 exams, 1 and 3 in 100%, and then the second one to be 30%. I think this is just what my decision is right now. There's no other option. I can add some other options, but I think we are really enough just busy. I can just add one project. I can define one just open problem. that you can do as undergrad students, but that's just really for now. At this point, I just say it's a lot of work for you. Make sense, Eduardo?
Yeah, I got it. Thank you.
Any comment for me? Can we just replace the in-class exam 3 for exam number 2? I really like this chapter. You mean the topic? What is exam 3? So you haven't seen exam 3. You will love exam 3 too. Don't worry. We don't have that much. I mean, as long as the topics that we are covering for the linear algebra classes. So remember, chapter 2 is just the fun one, which is invertible matrices. Then chapter 5 is diagonalizable. And we jump to the chapter 7, which is just the Jordan canonical form. That's just a fun one because it's following the same as the diagonalizable. That's why I go there. And the last chapter that we cover really shortly, is just really a short chapter. We can't touch that much, is inner product. If you've seen inner product before, I mean, because it's calculation, not proof that much, like dot product that we've seen in calculus classes, I think you will be fine there too. At the beginning of linear algebra classes, the most, I will say, frustrated part that the students have on this course is just they can't adjust this type of matrices to the transformation. So whatever they have seen in matrices, now they just need to bring every single concept and just translate it in somehow to the transformation. So this is a little bit hard at the beginning. And then when you get to that point, everything makes sense for you. I'm pretty sure you won't have any problem with this course. This is not just really a challenging course, as long as you follow my lectures at the same time with the group works and quizzes. So it just really make you ready gradually for any of the tests or exams or courses that you need in future. So just keep going, okay? You're doing a great job. Any other question, guys? So that does it mean you don't have any problem with any of the assignments, any practice quizzes, anything in that online submission? Everything was fine?
I have a question on the practice quiz. On number 1, can you explain what the vector space is that it's providing?
This is number, so practice quiz of the one which is due tonight, right?
Yes, correct.
And what is you mean the size of your matrices?
No, can you go over like what the vector space actually is? It says P of X is a polynomial with degree 10. Okay. And it says that the derivative of -4 is equal to 0 and the second derivative of 2 is equal to 0. What is that? Like, what do you mean by that?
Who is talking? I'm just trying to call your name. Who is talking? Can you?
Hey, Ben. Sorry about that.
What was it?
Ben.
Ben. Okay, Ben. So that's it. So if you can just really let me write down here. So do I have my pen available? No, why not? Okay, so now it's fine. So when I say polynomial of degree 10, so when I say polynomial of degree 10, I meant to be really a0 plus a1x plus a2x to the second all the way to the a10, 0, 1, 2, a10x to the 10, okay? So if I just say derivative of this, so that means I'm losing the first one. So then I have a1x and then a2x squared and then all the way to the a10x to the 10. And then it says plug in the value of -4. So that means you have to say this is at -4 is plug in everything equals x to be -4 equals 0. So this is basically means you have one what is it, system of equation, because if you have the second derivative, you are missing this one too, And that's just really sorry. I forgot to left, just this is not there. This is true, okay? And then so on, okay? So then you have the second derivative. So this means you have started from this, and then and the rest of them is just some numbers, and x to the 10 equals 0, right? So basically that means you have a system of equation that is missing. If you plug in -4, this is missing. What happened? What happened for my lecture note? Gone. Sorry. For some reason. Okay. Are we good now? Okay. So did you understand what do I mean? So you have a polynomial of degree 10. You take the first derivative, you are missing your first coefficient, and then you plug in the to be -4, and then you get the second derivative, then you are missing 2, the first 2, and then you plug in 2, and then you have to solve it actually for A1, A2. So then your system of equation, if you just say there are 2 equations, and then 2 rows, 10 columns, huh? So then this is just going to be, for example, 1, that is missing 0, so this is 2, and then -4, and so on. Does it make sense? So then this is free, this is, sorry, basic variables, and then you have 8 many free variables.
Okay, thank you.
What's the size of matrix? 11, huh? Am I right? Because it started from A0 to the A10. So it's 11 many. So you have 11 columns, so you have no free variables. Sorry. And that's exactly what actually the numbers that I wrote, that's just somehow answering the questions. How many ends do I need to be isomorphism? Because you want to have a dimension of your vector space to be, that free variables is just the number of dimensions. Am I right? The number in your free variable is exactly the dimension of your vector space. Because you can factor them out, you can make your bases. Make sense?
Yeah, thank you.
Any question about anything? We have about 3 minutes to stop. I know this is a long one. I'm not going to just cut any part of this lecture note when it's recording. But if anyone has any technology or any time that can just bring this one to the Camtasia and just cut it the extra time and make it more useful, that's great. If not, Brian, can you, do you really type these lecture notes or no? Brian, are you there? No, you left.
Yeah, I'm here. Yeah, I do.
Right now or just later you type them?
I can type them today for you. That won't be a problem.
So I don't want to just spend, so you see, Brian, that you don't have to do any of these things, okay?
You know what? But it's something, I take the notes like that usually anyway. And like if I produce it, then I keep it, and you know, I get some experience. And I don't know, maybe if you have some other project that is bigger, like just is something I can even like showcase and put on my CV and be like, hey, you know, I can do this sort of thing. So.
Oh, okay. That's great. Okay, that's a very good idea. But in general, I don't want to put any responsibility on you to do something just because you have to type it. I will provide this any handwriting note for the students, and then if you have had any if you have had any time to type them, and if you had the typed version for yourself, that would be great if you can share with all of us. But again, you don't have to. Okay, so we are fine.
No, yeah, you can count on me. I'll get them done today.
I know, because we are all having many things to do for being online. Actually, we are saving time a lot, but I'm hoping just we can use that saving time. Usually, it's just wasting more when we have more time.
Yeah, it really that won't take me too long. Just make sure to post those, and I'll kind of read through them.
Okay.
And if I mean, if you want, I'll message you. I already sent you an email, so if it's helpful and you want to share some more stuff with me or whatever ahead of time, that really won't be a problem. Like I said, it's something I can put on my CV or like a letter of rec or whatever.
You know why? Because again, I didn't have the technology. I bought this laptop. I went to buy iPad, but there was no iPad in any store. So then I end up to buy just whatever you have in a store is just really Surface Pro. But the thing is, I don't have anything ready, so I'm really behind. So
I mean, it's really, the presentation's really good. Like I don't think I have any. I have an iPad, but I haven't really experimented with trying to like do the video where you are writing stuff down and it's catching it right away. So yeah,
so
like
everyone is happy about being at home doing the job. So if you don't have any problem, so we will continue in this way, okay? So, but I am still waiting for your feedback if anyone has anything. If not, we are just really good for today. Any question, guys? No? So see you on Wednesday, huh? See you on Wednesday for the other lecture. Okay. Bye. Have a good day. Bye, everyone. So I have to stop sharing and stop recording too, right?